In this lecture, we introduced the root finding technique called the fixed point method or the Picard method for finding solutions of the equation f of x equals 0. To get started with the method, we transform the equation f of x equals 0 into the equation x equals g of x. And so, if we are looking for the root x equals r, instead of directly solving the equation f of x equals 0, we look for the intersection point at x equals r between the graphs of g and the line x equals y, assuming of course that r equals g of r. The equation x equals g of x leads to the recursion a sub n plus 1 equals g of a sub n, where a sub n is the fixed point method's nth estimate for x equals r. Since r equals g of r is said to be a fixed point of g, and hence the name the fixed point method. We illustrate the recursion graphically. We start with the first estimate a sub 1 on the x-axis for x equals r. Then we find g of a sub 1 or proceed vertically from a sub 1 on the x-axis to the corresponding point on the graph of g. G of a sub 1 is the next estimate a sub 2. Then we follow the horizontal direction to the point a sub 2 on the graph of x equals y. Then we proceed vertically to the graph of g to find g of a sub 2. G of a sub 2 is a sub 3. From this point, we proceed horizontally to the next point a sub 3, etc., 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 alternating the vertical with the horizontal directions. The fixed point method seems to fail miserably with this choice of g of x, since the sequence of points generated by the method seems to be diverging away from the target intersection point at x equals r. Let's give it another try with a different g of x this time. We superimpose the line x equals y with the graph of g, since we are after an intersection point between the two curves. From the first estimate a sub 1, we proceed vertically to the graph of g to find g of a sub 1. G of a sub 1 is a sub 2. We proceed horizontally to the point a sub 2 on the line x equals y. Then we go vertically to the graph of g to find g of a sub 2. G of a sub 2 equals a sub 3. We proceed horizontally to the point a sub 3, etc., etc., etc. This choice of g of x seems more promising than the first choice of g of x, since the initial set of iterates spirals tighter towards the target intersection point. What we now look for is a sufficient condition or conditions which, when satisfied by g of x, will result in the convergence of the method. We first subtract r from each side of the recursion equation. R equals g of r, so that a sub n plus 1 minus r equals g of a sub n minus g of r. We assume that g prime exists, so that we can apply the mean value theorem to this last quantity. G of a sub n minus g of r should be equal to g prime of some value c times the quantity a sub n minus r. C is some real number between a sub n and r. We define the error value e sub n to be equal to a sub n minus r. A sub n plus 1 minus r is e sub n plus 1. We take the absolute value of each side. And so we have the absolute value of e sub n plus 1 equals the absolute value of g prime of c times the absolute value of e sub n. Now, if the absolute value of g prime of r is less than 1, and if g is continuous, then there should exist some positive real number delta, and the corresponding open interval centered at r, and whose endpoints are r minus delta and r plus delta, such that the absolute value of g prime of x is less than some value k which is less than 1, as long as x is inside this delta interval. This means that if the nth estimate a sub n is also within this delta interval, then the absolute value of g prime of c will be less than k. And so the absolute value of e sub n plus 1 is less than or equal to k times the absolute value of e sub n. Therefore, we should be able to compare the sequence of the absolute values of the e sub n's to a geometric sequence. This geometric sequence happens to have as its common ratio the value k. And because the absolute value of the common ratio k is less than 1, this geometric sequence converges to 0. And so does the sequence of the absolute values of the e sub n's. And therefore, the sequence of estimates a sub n must converge to R. For the case when the absolute value of g prime of r is greater than 1, we can apply a similar argument to prove the divergence from x equals r of the sequence of estimates, unless by some stroke of luck, one of the a sub n's ends up being equal to r. To summarize, if the absolute value of g prime of r is less than 1, the sequence of estimates converges to r if a sub 1 is close enough to r. If the absolute value of g prime of r is greater than 1, the sequence of estimates will not converge to r, that is, if a sub n is never equal to r. One can get mixed results when the absolute value of g prime of r equals 1. Take, for example, the equation sin x minus x equals 0, which can be reformulated into the equation sin x equals x, with sin x equal to g of x. The root is r equals 0, and g prime of 0, which is cosine 0, is 1. It is a good challenge exercise to show that the sequence of the a sub n's converges to r equals 0. One can start by showing that if a sub 1 is a small enough positive real number, then the a sub n's form a bounded decreasing sequence. If, on the other hand, a sub 1 starts out as a small enough negative real number, then the a sub n's form a bounded increasing sequence. In contrast, the reformulation arc sin of x equals x, with arc sin of x equal to g of x, has the a sub n's diverging from r equals 0. The viewer can verify that g prime of 0 is still equal to 1. To prove the divergence of the sequence of the a sub n's, the viewer can show that if a sub 1 is non-zero, the sequence of the absolute values of the a sub n's initially increase and eventually become undefined as soon as the absolute value of a sub n becomes greater than 1.